Hi to everyone and welcome to this International Society of Automation webinar. My name is Rich and I'm a Senior Manager with IEEE Global Spec, and I'd like to review just a few housekeeping items with you before we get started. We're going to take a moment to familiarize ourselves with the operation of the user interface for today's webinar. Now, the large window that you're currently viewing with the heading presentation in the upper left, that's the primary window for the webinar. If you look to the right of that main presentation window, you should see the speaker's bio window, and that contains background information on today's presenter. Now, just below that, you should see the Q&A window, and at any time during this presentation, you can enter a question into the box in the lower section of the window and then click Submit. Your question will then be placed in a queue for our speaker to address when we get to that Q&A session. Now, if you look to the bottom of your screen, you should see additional buttons that will help enhance your webinar experience. Now, if you'd like to see what a particular button does, just hover your mouse pointer over it and a tooltip will appear with a description of that button's function. Okay, right now to get this webinar started, I'd like to pass things along to today's presenter from AE Solutions, Paul Gruen. Paul, go right ahead.
Welcome to this webinar, an introduction to safety instrumented systems in the process industries. My name is Paul Gruen, so who am I to speak on this subject? This is my title with AE Solutions. I've been involved with safety instrumented systems for 30 years. Very active with ISA, and they made me a Life Fellow for my activities and developments with safety systems. I am a longtime member and co-chair of the ISA 84 committee, which is the group that wrote the first standard on this subject, published in 1996. We're still an active committee writing a lot of additional stuff, as well as revisions to the standard and technical reports. I'm the developer and primary instructor for the ISA courses on this subject, primary author of the ISA book, which a third edition is about to come out, developer of the first commercial software modeling package for safety systems 25 years ago. There's a number of organizations that have software similar to that now. A licensed professional engineer in Texas and a member of the control system engineer exam team. A certified functional safety expert and an ISA 84 expert, two different qualifications from two different groups, and currently the 2018 ISA President-elect Secretary. So the topic is safety instrumented systems. What are they? What is that name? Common name for these in the past was ESD, not for electrostatic discharge, but for emergency shutdown system. And a lot of people didn't like the word emergency, bad connotation. So it was somewhat softened up in the mid-90s as a safety interlock system and then to a safety instrumented system. But before we consider that, let's look at the control system, which we're being generic and having acronyms here, the basic process control system, as opposed to the advanced process control system. But the control system could be pneumatics, it could be single loop controllers, it could be PLCs, programmable logic controllers, it could be a DCS, distributed control system. A lot of vendors don't like those names anymore, feel it's archaic, so they have new names now, process automation controllers. A lot of marketing and sales, but the systems obviously have changed and improved technologies over time. But the basic process control system is controlling temperature, pressure, level, flow, all of your other variables, keeping things within their normal ranges, so its own sensors, logic solver, and final elements. Simple question to all of you, how many of you believe the control system is perfect and will never fail? Because if that were the case, we would never have a single alarm. There would be no need for relief systems, scrubbers, flares. There'd be no need for fire and gas systems because nothing would ever be released. And you wouldn't need plant sirens and alarms because nothing would ever go wrong. But obviously that's not the reality we live in. We can't envision all scenarios and everything fails. It's just a matter of when. So when the control loop fails or is in bypass, how are you going to maintain safety if some variable goes outside its normal range? Well, in terms of instrumentation, we can have a safety instrumented system, which typically has its own sensors, its own final elements, and its own logic that does not control anything. It just monitors those variables to see if they're outside the normal range, and if so, it will bring the equipment and or the process to a safe state. These systems can be basically any technology, from relays, pneumatics, to solid-state systems that don't use software and software-based systems. Some of these systems are certified. Not all devices need to be certified. So the control system, being an active dynamic system, does not really require testing. We all know when it's working and we all know when it fails because it usually affects production pretty quickly, and your analog values aren't really being analog anymore, and production tends to be affected pretty quickly. But because the safety system is a passive or dormant system, not all failures are self-revealing. An isolation valve that's open all year round might be stuck. A pressure switch that only activates when it goes high, when pressure level goes high, what if it's stuck and not responding? You will only know either when there's a demand and it doesn't work, which is not going to be good, or you have to periodically test these systems to be assured that they will work when you need them. Now, there have been a variety of failures of control and safety systems that have resulted in accidents. This is a summary of a book that was first published close to 20 years ago and has been republished, new editions, and it summarizes, I believe it was 36 accidents that were the direct result of control and safety system failures in a variety of different industries. And the majority of problems came from incorrect and incomplete specifications. Where there was a specification, it just wasn't as thorough as it needed to be, or it wasn't really correct. I know one example where a safety system shut the plant down and the specification just said all outputs will de-energize, which they did, including the outputs for the lubricating oil pumps on the turbines, meaning the turbines self-destruct when they spin down, and now you can't run your process anymore without your turbines. So the system did exactly what it was programmed and configured to do. There was no failure of the system. There was a failure in the specification, because any system could have had those outputs fail on or a last state. This still remains the majority of problems with systems today. The next largest percentage came with changes after commissioning and startup, where one person thought it was a minor, insignificant change, was not properly reviewed by the appropriate people, and bad things happened. This is the issue of management of change, how a change to a line of logic, a procedure, a piece of hardware, anything must be reviewed by the qualified team and assess anything that could possibly go wrong and what the impact of that might be. There's a phrase, the road to hell is paved with good intentions, and many of those good intentions were changes made to keep the unit running, to prevent some other sort of problem, and that by itself introduced a longer-term problem down the road. Next largest percent were design and implementation problems, where the specification was correct, but the system was not built properly and was not thoroughly tested to find that problem. Operations and maintenance, where I know examples where they went to replace a sensor, they closed the isolation valve, replaced the sensor, and walk away, forgetting to open the isolation valve. So the sensor is now blind to the process. Not good. And even changes during installation and commissioning, where things were not installed per the manufacturer's recommendations. I know one end user reported in a study that 80% of instrumentation failures were reported back to the root cause, which was not installed per manufacturer's recommendations. So this is the book from the United Kingdom Health and Safety Executive called Out of Control, Why Control Systems Go Wrong and How to Prevent Failure. A very interesting read, and what they found is still relevant today. I've been involved with this for 30 years and have spoken to many project engineers and people I've worked with, and still most of the specifications people produce and the vendors and the integrators get are incomplete. That causes problems. It doesn't matter how many redundant certified devices you put in, it won't matter unless the specification is correct. Now, we realize in industry we need to try and solve all of these problems, so we have written documents to try and do that. And because we've had various accidents around the world, regulations have changed around the world. And in the U.S., we have the OSHA, Occupational Safety and Health Administration, PSM, Process Safety Management Regulation of Highly Hazardous Chemicals, that came out in 1992 because of a number of serious accidents we had in the U.S., and this affects any facility with 10,000 pounds or more of flammable combustible materials. And that regulation says you must follow industry standards. In terms of safety instrumented systems, the standard that OSHA accepts is the ISA 84 standard, which first came out in 1996 as ISA 84. Then the IEC, the International Electrotechnical Commission, started writing functional safety standards as well, and they produced 61511 for the process industry. There's a higher level standard that covers all industries. There's one for nuclear and one for transportation and one for machinery, one for process. And the process safety standard is 61511, which was released internationally in 2003. The ISA 84 committee added one sentence to it called the grandfather clause. What do you do about existing systems? And we published it and released it 1 year later in 2004. Now be aware that the IEC has released a new edition in 2016, but Part 1 was the incorrect version, so they have released a corrigendum, a list of corrections, as well as an amendment, further list of corrections. The 84 committee has reviewed that, and we have accepted the standard, and it will be released in 2018 as ISA 61511. We have not made any changes or added anything to the IEC standard. In Clause 1, the scope of the standard, it states in the very first sentence that it is an international standard that covers the specification, design, installation, operation, and maintenance of safety instrumented systems. Now, this applies to everyone who is involved with a safety system in any way, from the end user to even portions apply to the vendor in a sense if they are doing the system integration, to the engineering firm. There's management, there's engineering, there's operations, there's maintenance. Everybody involved, there's portions of the standard that apply to them. Clause 1A says you have to comply to this standard, but it does not mandate who is going to be responsible for what steps. It is up to the team and the end user to say, well, we're going to do this, and the contractor is going to do this, and the system integrator is going to do that, and the consultant is going to do this, and everything else, to make sure nothing falls through the proverbial cracks, because systems are large, many organizations are typically involved, and we don't want things to fall between the cracks. That's the lessons learned that these standards provide. Please don't look at standards like this as making your life more difficult, making things more onerous and problematic. These are standards based on lessons learned in blood, by accidents that have happened around the world, and the lessons learned have been documented by the people in the organizations involved with these accidents. And we've all documented our knowledge to help make the world a safer place. That's what these standards provide. Clause 1E basically defines what the process industry is. And the 2016 and latest version of the standard now adds food and pharmaceutical as well, because they can handle some nasty chemicals. This is the scope, part 1 of the standard. Nothing mandatory really in the scope. It just says who it applies to and that you need to follow all this. Clause 2 is on references to other standards. Clause 3 is acronyms and definitions, more than a dozen pages on definitions. Clause 4 is a conformance statement saying to conform to this standard, you need to conform to clauses 5 through 19. Clause 5, the first most important clause, is several pages on management. As Trevor Kletz, one of the founding fathers of process safety, who unfortunately is no longer with us, is famous for saying all accidents are due to bad management. Now, that doesn't mean bad evil management, it just means bad ineffective management. So we've tried to document what needs to be done for management to be more effective. There needs to be a policy and a strategy for achieving safety, as well as a means for determining how well you're doing and broadcasting that within the organization. So simply having a high-level statement of safety as our number one goal is not adequate. Simply saying no harm to the people, the equipment, or the environment is inadequate if you're violating it on a daily basis and not even monitoring to see that you're not meeting that. Simply saying the number of lost days or number of days since a lost work or injury has nothing to do with process or functional safety. The departments within your organizations who are going to be responsible for the various tasks need to be identified, and they need to be told these are the tasks you're responsible for. And the people in those departments who are going to do those tasks need to be aware of what they're responsible for. And those people need to be competent and qualified. And here are some of the bullet items listed in the standard of how you can judge someone's competence. Hence, listening to a seminar like this increases your level of awareness. But if you really need to be or become competent in designing and being involved with safety instrumented systems, you will need to read the standard and or read a book about it and or take a class that are typically 4 days long. Simply attending a one-day seminar or something shorter will give you an awareness, but will not make you competent to do any of the work that is actually described in the standard. Periodic audits need to be done to make sure you're actually doing what you said you've been doing, and there needs to be an assessment by a qualified team to make sure that what you're doing is adequate, that your SIL selections are being done properly, that your testing procedures are actually thorough, and the testing actually has written procedures on how to do it, and records are being kept. And that assessment team needs to have a senior, competent person not involved with the project, because the project and the team members won't see or admit to their own mistakes. And a senior, competent person who has the authority to stop the project from proceeding. You feel, hey, we need to start the unit up tomorrow, and we're all in a rush, and we have a schedule to meet, and the auditor or the assessor looks at these 36-inch valves that your specification says must close in half a second or less, but you just have a standard solenoid-operated valve with a 1/4-inch vent line, and that 36-inch valve takes a minute to close, and that senior competent person says, sorry, you can't start the unit. I don't care what your schedule or the cost is. That system is there for a reason, and it won't work. I'll spend a lot of time on this slide that talks about all the clause numbers in the standard, and rather than just have individual slides, we can describe them generally here. Now it's the life cycle, the set of steps or activities that you need to do, and this is clause 6 of the standard that summarizes the life cycle, and then clause 7 through 19 go through all the details. But a graphic here is worth 1,000 words, and I may use easily 1,000 words on this slide. Now, some of the steps described in the standard are things you have to do, but the standard does not tell you how to do them. So a hazard and risk assessment, there are plenty of other books and standards that cover that. But you have to do that, and that leads you to the design of your safety instrument system and all the individual safety instrumented functions. Where you're going to need a high-pressure shutdown to prevent an explosion, a high-level shutdown to prevent overfilling a vessel, a low-level shutdown to prevent overpressuring a tank if you get low level in it and you get blow through or damaging downstream equipment, whatever the case is. Now the numbers in the boxes are the clause numbers in the standard that go through more detail on this. Clause 5 was on management. You'll see how that is going to be shown. We'll see all the clause numbers eventually. Once you've done the hazard and risk assessment and you identify the safety instrumented functions you need, well, actually that's coming here in Clause 9, you allocate what are we going to do? What safety layers might we have to prevent overpressure or high level or low flow or whatever the case is? Where can we use relief devices, scrubbers and flares and containment areas and alarms and flares and fire and gas and everything else? So here we determine, okay, well, we do need some safety instrumented functions, and we determine the SIL, the safety integrity level that each safety instrumented function needs to meet, which I'll get into this more in an upcoming slide. And all of these are really outside the scope of the standard. It's the process engineers and other documents that talk about how to do all this, but they are necessary steps that lead you to the design of a safety instrumented system. And actually, methods of determining SIL, safety integrity level, is covered in Part 3 of the standard. It's a 3-part standard. Part 1 is normative, the requirements. Part 2 is informative, that explains Part 1. And Part 3 is informative, that it summarizes different SIL, safety integrity level selection techniques used around the world. When you decide you need safety instrumented functions and have SIL targets for them, you now need to overcome that 44% of the problems that were incorrect and incomplete specifications by developing a thorough and complete safety requirements specification, which is Clause 10, the 2 most important pages in the standard. Now, the 2003-2004 version of the standard had part of the software lifecycle in Clause 12 on software. But the 2016 and 2018 versions of the standard, that's all been, as far as lifecycle activities, have been included in Clause 10. And the requirement specification is not saying buy brand X. It's saying, I don't care whether you buy brand X, Y, or Z, this is what the system has to do. It's completely independent of the implementation solution or what you select to meet the specification. Clause 11 is detailed requirements in hardware design, how you respond to faults, fault tolerance issues, interface issues, bypasses, all sorts of things. Clause 12 on software design. And that's about the only thing that falls on the system integrator, is the actual building of the system to the specification that they should have received from other parties. The system gets installed, it gets commissioned to make sure everything's working properly, and the system is validated, which is comparing the actual installed system against the requirement specification, that all the I/O are there, it functions as intended with the speed of requirements, all the bypasses work, everything communicates to other systems. That's validation, because the difference in time between when the requirements are solidified versus installation and validation may be years. And we want to make sure that the system meets the specification, that things have not inadvertently changed, potentially for the worse. Clause 13 you might see is missing. That's the factory acceptance test, which in the 2003 and 4 versions of the standard was informational, not an absolute requirement. But in the 2016 and 18 versions of the standard, Clause 13, the factory acceptance test is mandatory. Clause 16 on operation and maintenance is the longest time of the life cycle, 15, 20 years or more, where the system is operational, and you have to have periodic testing, proof testing procedures, and inspection procedures. Throughout that 15, 20, or whatever the lifetime of the system is, you will obviously make modifications and changes at some point, and that has to go through proper management of change reviews, and even taking a system out of service. There are things you're expected to do to make sure no other functions are affected. Anything that needs to remain operational will, and when you shut this one unit down, you don't affect other process units. Clause 19 is on documentation. There's not a separate box shown for just the documentation that you're expected to produce overall. But Clause 5 is on management, the assessments, and audits that we covered earlier, and that applies throughout the entire life cycle, which is what this longer, taller box is intended to try and convey. Verification is different than validation. Verification is to make sure each and every one of these steps is done. It's done properly. It's done with the right people, that you have the right information or documentation to do each individual step or box shown, and that the team produces the right documentation that people downstream are going to need afterwards to design and build and operate the systems. So verifying, see the E in verify and the first letter E in the word each, that each step was done. That's verification. Validation is only done once. That's the check that the installed system actually meets the requirement specification. So the overall life cycle to, once again, make sure nothing falls through the cracks between all the different organizations that are going to be involved in this project over years of time. One of those boxes talks about determining the required safety integrity levels. There are many methods for determining what safety integrity level each individual safety instrumented function needs to meet. Part 3 of the standard describes many techniques used around the world, but the page-and-a-half introduction clearly states that even this close to 80-page document does not adequately describe any of these methods in detail. Not enough detail to actually use. They're simple, high-level summaries. Now, in a short webinar like this, I don't have time to go through some of the more detailed methods, which are more preferred within industry. The most preferred technique is called LOPA, Layer Protection Analysis, but it just takes too long to try and cover here. There are 2 annexes that talk about risk graphs that have traditionally been more common in Europe, but have been done with some in the US. And it's a simple idea that it's easy to have one graph and one slide to get this idea across. Now we start on the left with the consequence factors, CA through CD. Now, this would be an example of a risk graph for personnel safety. But you could have a similar risk graph for environmental, where there's different consequences for the size of the environmental release, or the consequence category could be for commercial reasons, commercial integrity levels, whether it's lost production downtime or capital equipment losses, just as people do EIL, environmental integrity level. Let's say we have an accident where there might be, the wording here is obviously horribly vague to use effectively, but let's say there's several deaths. So we start on C sub C on the left. Then we look at what is the frequency and exposure of the personnel to this hazard or hazardous event. One of the annexes has this horribly vague wording. Another has a bit more precise wording and mentions, well, it's 10% or less, or potentially 10% or more. And let's say it's normally an unmanned area of the plant, so let's say it's FA, rare to frequent. So we started on C sub C, then we're at F sub A. Then we look at the possibility of the people avoiding this hazardous event. Now, there are a number of factors to consider. The level of training of the people, how quickly the process hazard will develop. It's a basis of the process safety time, PST, not for partial stroke testing of valves, but process safety time. How quickly will the hazard or the process go hazardous if you lose all control? What level of alarms and indicators do people have to be aware of that? What level of manual means do they have to bring the process to a safe state, and do they have enough time? Are there safe havens for them to escape to? A variety of factors to consider. And let's say we meet all these criteria, and therefore it is sometimes possible to avoid this event. So now we're on line P sub A, working our way through the left side of that risk graph. The last factor, the W columns, are the probability of occurrence, which is stated in both annexes. It's the demand rate on the safety instrumented system. And if you didn't have the safety system, it would be how often the accident would happen if you didn't have the safety system. Sometimes these numbers may be difficult to come up with, and one of the annexes does have this horribly vague wording, which again is too vague to effectively use. It's just trying to show an example. You still have to develop more detail with this. But let's just say we choose the middle category, slight. So we started on the left, C sub C, then F sub A, then P sub A, the middle column. We need SIL 1. The numbers in the boxes are SIL, safety integrity levels. So this function to prevent whatever high pressure that might cause several deaths, which people can, typically they're not around, and there is some ways to avoid it, and chance of it occurring is just slight. This function needs to meet SIL, safety integrity level 1. So what does that mean? SIL is a discrete number, 1 through 4, and it is a measure of function performance. Not the whole 200 IO system, but the individual safety instrumented function, which consists of a sensor, a logic, and a final element. Now, the 1996 first version of the standard had the term PFD, probability of failure on demand, but the numbers are so small you have to use scientific notation. And I do classes where I give people pieces of paper. I write a number on the board, 0.005. And I ask them, write down 1, 2, 3, or 4, depending upon what integrity level you think that number falls in the PFD range, 0.005. Go ahead and mentally do that for a second. And in the 1996 version of the standard, we had the complement, 1 minus that. We called it then the safety availability, which was not a good term, and that term no longer exists. With that one, you just end up with this endless stream of 9s, which most people don't relate to either. Most people don't see a significant difference between 99% and 99.99. To most people, that's less than 1%. Oh, well, it's 2 orders of magnitude different. It's just not easy for most people to see. So there was one guy who's retired now, and he came up with one over the PFD, and industry now refers to that as the risk reduction factor. And that 0.005, you take the reciprocal, and it's 200. I've had large groups, when I give them that 0.005, I've had people say SIL 4, some say SIL 3, some say SIL 2, some say SIL 1. I've had groups where the majority of the group got it wrong. But if I tell you the risk reduction is 200, what integrity level does that fall into? I get a classroom of 10-year-olds, and they'll all get that one correct. So risk reduction factor is the preferred term for most organizations. But what does it take to design a system to meet SIL 1, SIL 2, SIL 3? That's where money comes in. And that's where fault tolerance and various terms like hardware fault tolerance, safe failure fraction, there's a significant difference in different technologies that will meet all of these different performance requirements. Now, it's worth mentioning the earlier version of the standard, or the original 1996 version, only went up to SIL 3. And there was a book from the American Institute of Chemical Engineers, from the Center for Chemical Process Safety, that also addressed these topics back in '93. And that book only went up to SIL 3. We knew there was SIL 4 in the higher level IEC standard. We all stated and thought, well, that's aerospace, that's nuclear, that's transportation. God forbid that's not the process industry. We just don't design things like that. But there was one powerful end user in Europe who did get SIL 4 put in the standard, and I don't know anyone other than him or that group, that company, that might have had a SIL 4 requirement. Most people, and the standard's actually very clear now, if you have SIL 4, rethink that. Redesign the process to be inherently safer. I mean, there's no reasonable way to put in instrumentation that you actually think is going to work 9,999 times out of 10,000 demands. It's like, please. I mean, if you factor in people, you won't even come close to that, and maintenance issues and everything else. It's much more than just analyzing the probability of device failure. There's a whole lot more that's involved with all these numbers. It's more than just statistical number crunching. I know people in the process industries and the refining industry who say they don't even have any SIL 3. Just because they may have high risk doesn't mean you have high safety integrity level requirements. Think of all the other multiple independent protection layers you have, and doing an appropriate SIL selection review, that you should not really have even SIL 3 requirements. I would probably say 70 to 80% of most functions in the process industries are SIL 1. The remainder are basically SIL 2. A lot of those are fired equipment, because also when you look at burner management and various standards, they have mandated for a long time redundant sensors and redundant valves and logic solvers that have certain levels of diagnostics. They're clearly stating a SIL 2 design, even though they may not have used that term in the past. Although actually now all the NFPA and various burner management standards now acknowledge alternative performance-based design. They specifically mention ISA 84. And the idea of SIL, safety integrity level. So when we're talking about PFD, probability of failure on demand, we're really talking about one particular failure mode of systems. And safety systems can actually have two failure modes. There have been people who had relay safety systems replace the relays with PLCs, implemented the same logic, thought they made an improvement with the newer technology, and they had accidents because they did not understand this extremely important concept. The main idea is not so much how does the system operates, how does it fail. And safety systems, it's somewhat of a simplification, but safety systems can fail two ways. There are what industry calls safe failures, where there is nothing wrong with the process. There is no high pressure, but your normally energized function has a wire that falls off a connector, or a power supply fails, or a solenoid burns out, and the function activates when you did not want it to, and it shuts the entire process down. This is termed nuisance trips, spurious trip. The standard refers to this as a safe failure, although everyone admits there's nothing safe about a nuisance trip in a process plant. The most hazardous time of being in a process plant is when you shut down and start up. The main concern is lost production downtime in economics. This has nothing to do with SIL, safety integrity levels, although there are safety issues involved. SIL, safety integrity level, is a measure of PFD, probability of failure on demand. So it's the idea of the pressure switch is stuck. The relays are stuck. The PLC is hung up in an endless loop and is stuck. The I/O circuits are stuck, energized. The solenoid is stuck. The solenoid works, but the valve body is stuck. These are all dangerous failures. Actually, they're potentially dangerous. Just because the isolation valve that's been open for the last 2 years and now it's stuck, that does not immediately cause a hazardous event. If there is a demand at the same time that the device is unavailable to do its job, that's when you might have your hazardous event, as that little equation and graphic shows. And because you want to find these failures before you have the hazardous event, these systems must be tested, because These are passive, dormant systems. The valve never moves. The relays never change state. The only way you'll know if it's working is by testing. And proof test intervals are part of the PFD, probability of failure on demand calculation. So in order to prevent the 44% of the documented problems of control and safety systems is to get the safety requirement specification as correct and as thorough as possible. The two most important pages of the standard that lists, now with the latest version, almost 36 things that have to be documented for each and every safety instrumented function. Again, these are lessons learned the hard way through blood and accidents. So we're not saying we're trying to make your life more difficult by making you document these 36 things. It's you will be safer and you will have a system that is correct from the start if you document all this and avoid the potential accidents that so many others have had. Now, I don't have the space nor really the time here to go through 36 bullet points. I'll list kind of the major obvious ones here. This system has to bring the equipment or the process to a safe state. You don't really think the vendor or the system integrator knows what the safe state of your process is, so you need to document that. By any potential common cause problems could be like plugging or severe corrosive service. If it's plugging service and high temperature, you don't want 10-meter long impulse lines of 1/4-inch tubing. They're going to plug on the first day. You need to specify all the materials of construction to make sure things don't corrode and fail within the first month. Common cause, a single stressor or failure that wipes out multiple things. What are the inputs to the safety system? The integrator doesn't know what inputs you need. They certainly don't know what trip points or shutdown values or alarm values you're going to have. And again, the specification here is the requirements. It's not the implementation. It's not buy brand X logic solver and brand Y sensors. That's not a specification. You need to tell those vendors and system integrators what their system needs to do, because this can go to every system integrator and they'll all provide you a different solution, but they all need to meet this requirement specification. What are all the outputs? What are valves, pumps, motors? What goes on? What goes off? What energizes? What de-energizes? What functional logic, timers, latches and resets, and how will bypasses be done? You have triplicated transmitters. How will you do discrepancy alarms? And how will bypassing one affect the logic of the others? Response time. Do you actually have 36-inch valves that have to close in half a second? I have seen such requirements in different industries. Imagine you forgot to specify that. I know of a $100 million loss in the space program because there was something that all the mechanical designers knew, but they didn't document, and the software programmers did not understand the hardware, and oops, sorry, the satellite crashed, and a lot of lost money and time. How will you do a manual shutdown? What if the logic system is not working, and how will you do a manual shutdown? Is it a local button out in the plant that somebody could do, or is it a remote push button on a control system screen somewhere? The integrator has no idea what you need to do here. You need to tell them what you want based on your unique process. What, if any, kind of human-machine interface are you going to have? Many safety systems do not have a standalone interface. They communicate to the control system, and the operators build up the screens they want there. But it's important to have proper displays. ISA does have a new standard on this and is writing additional technical reports. And there's some really good books on high-performance human-machine interfaces. Because if you have screens that are a P&ID, piping and instrument diagram representation of your process, with 40 or 50 numbers sprinkled on the screen, numbers showing flow, level, pressure, and you have red and green for pumps and valves that are on and off and open and closed, you have the world's worst HMI that will cause an accident eventually. We have learned the hard way and through plenty of industry studies what it makes an effective HMI. That's a whole topic all by itself. If the system shuts down, you have a burner management system and you get high pressure and you get a flame out, and when pressure in the system shuts down, valves close. When pressure comes back to normal, do you want the valves automatically reopening? No. So how will resets be done? Because it's unique for each application and process, and the integrator has no idea what you need. So this needs to be specified in detail. You have to document the safety integrity level of each safety instrumented function, and certainly end users are concerned about reliability or spurious trips and unnecessary shutdowns. And it is in your best interest to specify what you want as a no more nuisance trips than X, or 10-year minimum time between nuisance trips on average according to a calculation. Because I can have the world's safest system and it can give you a nuisance trip once a week, meeting very, very high risk reduction factors I can do at the expense of lousy nuisance trip performance. So you probably want to specify both. And then when it comes to designing systems, what will you actually do to meet SIL 1 through SIL 3? SIL 4 I basically don't even show because no one would recommend having SIL 4, and it's just incredibly difficult to design. And in reality, it's not even possible if you want to include human error rates and maintenance issues and people leaving things in bypass and not following procedures. Most people just simply do not design for SIL 4 and would redesign the process to be inherently safer, add other safety layers, so you don't even have a SIL 3 requirement, let alone SIL 4, because you'll see here how expensive and difficult SIL 3 is. Now this is what we might term a cookbook based on the set of assumptions here: yearly testing, just one input and one output. Now those inputs and outputs might be fault tolerant or redundant, but it's still just one input pressure and one output shut flow. But I might measure pressure with multiple sensors and shut flow with multiple valves. Now SIL, Safety Integrity Level 1, can be done with just about anything, and non-redundant stuff, switches or transmitters, about any logic solver and standard valves. But if you have a 5-year test interval, you probably don't even meet SIL 1. So if you think, well, we have a 5-year turnaround period, then you need to build a new cookbook based on actually doing PFD, probability of failure on demand calculations, to see what is it going to take for your design based on your hardware and your practices. But systems need to be tested much more often than every 5 years, I'll simply put it that way. SIL 2 tends to get expensive. Now, I have not covered the fault tolerance tables in the standard and other more details like safe failure fraction. There just isn't time. But the tables in the standard show to meet SIL 2, you need fault tolerant field devices, sensors, and final elements. The 2003 and 4 version of the standard clearly shows that, although there's exceptions to every rule that I've even covered on this slide. 2016 and 18 version of the standard, you have to understand the wording that accompanies the table. The table looks a little different, but the wording, if you understand it, it's really then the same as the old table. Because SIL 2 could be done with single devices if you know what you're doing. I could select safety-certified devices that, based on the higher level of diagnostics, meet SIL 2, but you still must read the vendor's safety manual in understanding on how you have to configure, maintain, proof test, and operate that device. If you don't follow the vendor's manual, it doesn't meet SIL anything. You can have fault-tolerant sensors, 1 or 2 sensors. That's dramatically increasing your price, or cost, installed cost, and operating cost. General-purpose PLCs you can rule out. They're typically not going to meet your typical general-purpose PLC. Final elements is either going to get into partial stroking of valves, which allows you to meet SIL 2 now with a single valve, or fault-tolerant valves, 2 valves in series for shutting off flow. Or maybe just 2 valves with quarterly testing, so maybe you don't even do the partial stroking. There's a variety of ways of doing this. It is a performance-based standard. It does not prescribe in detail, well, you must implement this hardware and this configuration and this test interval. No, you get to decide and document it based on a calculation that shows this is safe enough. Now, the jump from SIL 1 to SIL 2 is approximately $50,000 total installed cost. That's just installed cost of putting in another sensor, another valve, all the engineering, all the installation, everything else. That's not even including the operational cost over a 15 or 20-year life. SIL 3, and that's $50,000 per function. Jumping from SIL 2 to SIL 3 is typically another $50,000 because here the standard design is triplicated transmitters. Triplicated switches aren't good enough. Logic solvers, you can rule out any kind of general purpose PLC, and you're not even going to be allowed to use a safety configured general purpose PLC. Everyone would use third-party certified for use in SIL 3 safety PLCs, which are much different than general-purpose devices in that they have much higher levels of diagnostics. But hey, there are relays. There are solid-state devices that actually meet SIL 4 and SIL 3 as well. The valves tend to get very difficult now. This is where a lot of expense comes in. There have been people that have implemented 3 valves in series, or 2 valves with quarterly testing, or 2 valves with partial stroking. A single valve is very, very unlikely to meet SIL 3, no matter what the vendor might say, no matter what their certificate might say from the assessor based on failure rate, that if you understand the numbers you're looking at, you'll realize how, I'll just say, unbelievable certain data and certain certificates are. So be leery and cautious of what certain vendors may say. That's why people have to be competent and qualified to do this work, not just taking every vendor for their word. And you can attend longer classes that are typically 4 days, where you can learn how to do all these calculations and all the background with everything that I'm describing here. You can see SIL 3 is very, very difficult. Now, I remember one email from on the ISA safety list serve of close to 800 people, and there was a guy who was offshore India with an offshore platform saying he has 3,000 safety IO that he's been told he needs to design to SIL 3. And he's asking, well, 800 people in this online community, how do I do that? And I emailed him back, here's how you do SIL 3. Now, do you think anyone would do that for 3,000 IO inputs and outputs on an offshore platform? Obviously not. No one ever has, and no one ever will. And I emailed him that. And I said, you don't have such a requirement. You have someone somewhere in your company who went to a seminar and heard SIL 3 is the highest without having any understanding of what that means or what it costs. And he comes back to you and tells you to do everything for SIL 3. Well, I'm sorry, that's just not possible, and nobody can afford to do that. So that's been a summary of the standard and what the life cycle is and what safety integrity levels are and what the safety requirement specification is and entails and what it takes to design SIL 1, SIL 2, and SIL 3. So if you have any questions, you can pose them, and if I'm unable to get to them in the next 10 or 12 minutes with the remaining time that we have left, there's my email. I will do my best in a timely manner to answer your questions. I have had on occasion in the past where people ask a very simple question, but the answer is, read the book. Or this is an entire chapter in a book, or read the standard. I mean, they're asking for something in detail, explain. I'm sorry, that's not possible in an email. I'll do my best, though.
Okay, Paul, thanks very much for moving us into the Q&A section. Now, quickly, before we start, I'd like to just remind everyone, if we don't get to your question, don't worry. As Paul mentioned, we will have an answer for you following the webinar. Also, the complete Q&A transcript, including answers we don't have time for, will be sent to all of our registered attendees and will be posted with the webinar when it goes into the on-demand mode. Okay, now we're going to move on to that first question, Paul. Paul, this is related to something you mentioned earlier. What does the grandfather clause really mean, and what do I have to do to meet it?
That used to be clause 1.y, the one thing we added back in 2004 that differentiated ISA 84 from 61511. Actually, then it was ISA 84 in parentheses, IEC 61511 mod for modified. We added one sentence. So what do you do about all the systems that you installed in the 80s and early 90s before any of these standards were available? Well, around the world, you basically have to revalidate your PHAs, your process hazards analyses, every 3 to 5 years, depending upon where you are in the world. And now when you're revalidating, you have your P&IDs, your piping and instrument diagrams, and there's an ISA symbol that should be used for a safety instrumented function, even way back in the 80s and 90s. And hey, I see one of these diamond symbols, so there's a safety function. Oh, geez, we did not assign an integrity level to that in 1990. Let's do that now. Now, there's one worldwide organization that analyzed over 5,000 safety functions against this grandfather clause to see what they had and what they might need to alter, if anything. And they found almost half the functions that they originally had were over-designed. Well, you don't have to change that if you're willing to live with it. And almost half were no change required. It was just 4%, only 4%, that were originally under-designed and they would have to change. So, as I mentioned in the risk graph here, you look at that's one method of determining or selecting what SIL you need for all the functions that you have installed. And then you can learn to do the PFD, probability of failure on demand calculations, to see if your installed hardware, with its failure rate and its level of fault tolerance and its proof test interval, does it actually meet the SIL target that you've set? There's calculations, whether it's fault trees or Markov models or block diagrams or algebraic equations. And as an example, let's say maybe you have a SIL1 target and you've got a standard analog transmitter and you've been using some of these safety PLCs for decades, and you've got a single solenoid operated valve and everything's tested yearly. You're fine. That meets SIL1, no problem. You don't have to change anything, but simply saying that, well, we've had it there for 30 years, we haven't had any problems, it's grandfathered. No, that's not really what grandfathering means, because the clause says you have to determine and document that things are designed, operated, maintained in a safe manner.
Okay, Paul, thanks for that answer. Here's another question for you. It seems more and more people are specifying that field devices shall be SIL certified, yet others say it's not necessary. How can one meet the requirements of the standard?
Yes, certified devices are not a requirement, but I have seen more and more people, even discussing it online, saying, well, we specify that all of our safety devices shall be SIL certified. And everyone replies, that's not necessary. That's not even necessarily going to help. That's no guarantee that anything will work. I know of cases where they had a boiler and a very difficult drum level measurement, and they knew, based on experience, that only one technology will work. Oh, but their company standard said all devices must be SIL certified. They couldn't get that technology. No one had it that was SIL certified, so they used another level measurement that was. And a month later, they found it doesn't work. So just because you use SIL certified devices because you now have failure rate data from the vendor, well, failure rate for some devices like solenoids and valves and certain things is just garbage numbers if you understand what you're getting. Oh, the vendor cycled the device, the solenoid, 10 million times and they never saw it stick. So they therefore have an incredibly low failure rate, which is absolutely not appropriate for a low demand application where that device might maybe get stroked once a year for testing. Solenoid or a valve is going to have completely different failure characteristics comparing to cycling it daily versus cycling it yearly or, God forbid, every 5 years for a turnaround. So there can be a benefit in using certified devices, and that you're assured the vendor has gone through a good quality program and all the documentation that the standards talk about, but that alone is not going to solve your problem. And it doesn't absolve you from doing the rest of the life cycle, reading their safety manual and implementing all the things they say you have to do. Plenty of people have implemented these devices and not followed the vendor's manual. So it's like, look, you don't meet SIL anything. I'm sorry. And this is especially true with fire and gas systems, where more and more people are saying they want fire and gas detectors and valves and all this to be SIL 2 certified. It's like, oh, God, please tell me you're not actually claiming SIL 2, a risk reduction factor, somehow in your LOPA, your layer of protection analysis, and say we're now meeting our safety targets because we're putting in fire and gas functions to get us down to our required levels of risk. Oh, really? You mean it's okay to have fires, you're just going to put them out 99% of the time? Really? Really? Are you going to say that in public? If you don't have the right number of detectors in the right location, you won't even detect 80% of the leaks. You won't meet SIL anything. I don't care what the hardware is. It's detector coverage and mitigation effectiveness. I mean, you don't really think a fire and gas system would have prevented Bhopal, or even mitigated Bhopal, or Texas City, or Piper Alpha, or the Deepwater Horizon. Those are all massive gas releases and explosions, except Bhopal wasn't an explosion, and no fire and gas system in the world would have helped anything along those lines. The standard, you do not have to have certified devices. You can simply implement devices that you justify are good enough based on prior use. Now, the 2003 and 4 versions of the standard use the terms prior use and proven in use interchangeably. The latest 2016 and 18 versions of the standard show that proven in use is for the vendor to do, prior use is for the end user to do. But for you to do prior use, you have to have competence in the vendor's quality program. You have to have enough statistical evidence to have valid failure rate data that using these devices in this applications is suitable, and I can do, for example, a single device SIL 2 and still actually meet the hardware fault tolerance table requirements as well as meet the PFD calculation. So to summarize that one, you can use certified devices. It's not a requirement. Sometimes it doesn't help at all, and you can still justify devices based on prior use.
Okay, Paul, thanks very much for that answer. Now, Paul, this next question is related to something else that you did touch on. Many valve manufacturers are promoting the benefit of partial stroking of valves, yet many users have reported problems doing so. What is the issue?
I remember once years ago being the program chair in the Houston ISA section, and we had a monthly meeting on partial stroking of valves. This was more than 15 years ago, and I had 4 vendors that came in, did a little 5-minute blurb on each of their stuff, and then we just opened it up for Q&A. And I was amazed, even though I tried to ask them leading questions, the vendors themselves didn't understand the real reason why anyone would do partial stroking. Like, oh, you get diagnostics and you know when something's wrong with the valve and you fix it. It's like, no, you still don't quite get it. The main reason for doing partial stroking is twofold. Either A, you want to meet SIL 2 with a single valve rather than meet the fault tolerance requirements that say you need 2 valves, and putting in 2 24 or 36-inch valves costs a lot of money and takes a lot of space. Partial stroking of a single valve can achieve the same level of performance for a dramatically lower cost. Or maybe you do have a 5 or 7 year turnaround, and you'll never meet that with a single valve with just proof testing every 5 years. But if you can partial stroke the valve on a weekly, monthly, maybe quarterly basis, you can do the calculation, which you can learn in longer courses or use some of the software tools to show that even a single valve can now meet SIL 1 with a very long test interval. Now, there are multiple methods of doing partial stroking. There's very simple manual methods to very complex methods involving positioners and all sorts of intelligent devices. I've got literature from more than a dozen manufacturers of different methods of doing this. Now, a lot of people have been promoting this for close to 20 years, and some people have implemented it and had problems and turned the functionality off. I've had cases I know where it was designed, and once operations heard wind of, you want to do what with my valve online? And they won't even allow it to happen. Some cases where they're being inundated by so much raw data that they don't know how to interpret, and the valve performance changes over time as well, that they just turn it off and they're not happy with it, which now that brings a problem, because you design SIL 2 with a single valve and you're not doing the partial stroking. You don't meet SIL 2 anymore. What are you going to do now? There are vendors who have had success with it in a limited number of applications, and when I hear that they're doing it for like less than 5% of their functions. And again, there are multiple methods of doing this, and there's actually, we've written in the 84 committee a technical report that includes the modeling and discussion of this. There's the ISA 96 committee on valves that also has a technical report on how to do this, and the different methods and different level of diagnostic coverage you can get into. Different groups and technical reports cover this in slightly different ways and slightly different topics of partial stroking, but that's a big topic all by itself. So it has been done. You might try it in a pilot application or one limited application just to see how successful you are with it. And if you are successful, or talk to other peers within your industry, talk to the vendors, see what they have, because there's lots of different solutions. So there really isn't time to try and answer anything else. So again, if you have questions that I haven't gotten to, there is my email. Please feel free to forward it on, and I'll do my best. And I hope you enjoyed and got something useful out of this webinar. And thank you for your time.
Okay, thanks very much, Paul. And just a few things before we wrap up. We'd like to thank you for taking some time to be here with all of us today. And we'd like to say a special thank you to all of our audience members for being part of this webinar event. Now, we'd like to let everyone know that you'll be receiving an email from us with a link to the on-demand version of this presentation, a PDF of this PowerPoint, an FAQ document, and a Q&A transcript. Now, lastly, please take a moment to complete the survey, which will appear on your screen at the end of this live webinar. Now, for the on-demand viewers, you'll find the survey located along the bottom of your attendee console in the survey widget. Again, thanks for taking the time to attend this webinar event. Take care and have yourselves a great day.